So this is the band pass filter response. The band stop filter, it's totally the opposite. So we are blocking only certain band and the passing rest of the frequencies. So here we have stopping this one and passing the rest of the frequencies. So this is called band stop filter. Okay, so it means we are eliminating or rejecting certain frequency range. So here then definitely we will have two cutoff frequencies, F1 and F2 or FL or FH. So already we know that by just cascading low pass filters and high pass filters together, we can form a simple band pass filter that will pass a range or band of frequencies that is here. So what we are doing in the band stop filter, so we can also combine these low pass and high pass filter sections to produce another kind of frequency response or to produce another RC filter network that can form a band stop filter. So the purpose of this band stop filter is it can block or severely attenuate a band of frequencies within these two cutoff frequencies points. So here we can see here. So it severely blocking or stopping certain frequencies between these two cutoff frequencies, and it passes all the rest of the frequencies. So band stop filter functions exactly the opposite way to the band pass filter. So this is totally the opposite operation of this band pass. Okay, so in band pass filter also we have combined low pass filter and high pass filter. We just cascade them together. So here also we are combining this low pass and high pass, but we get the result is totally different. So how can we do that? Okay, so we talked about this band stop filter now. So if the stop band is very narrow and highly attenuated over a few hertz, then this band stop filter is most commonly known as Notch filter. So here you can see the bandwidth of the stop band. It's quite wide. So instead of having this kind of very wide band, if this band is very narrow, then the same band stop filter is called as a Notch filter. Okay, so the Notch filter frequency response is really very narrow, as you can see here. Okay, so now we will just move. We can combine these low pass filters and high pass filters together with a summer circuit to produce the band stop filter. So this is the difference between the band pass and band stop. In band pass, we do not have the summer circuit or adder circuit. We just cascaded this low pass and high pass together. So if you remember this, so we just cascaded this high pass and low pass and we formed this band pass filter. But here in the band stop filter, we are just combining these two filters, but together with adder circuit or summer circuit. So we already know how the summer circuit is working. We had seen in the operational amplifier applications, right? So op-amp applications, we had seen the operation of summer. Okay, so we are applying the input to low pass filter and high pass filter, and then we are getting the response of the low pass filter and high pass filter, and we are adding these frequency responses. That is, we are taking this and then giving us an input to the adder, and then we are getting the output. So what is the low pass filter frequency response? So just to try to remember, this is the low pass filter frequency response, right? So we are just getting frequency, passing the low frequency, and we are getting the output. And then at higher frequency, we are blocking. The output is 0. This is the low pass filter. And the high pass filter, what we are getting at the output. So it's just blocking the low frequencies, and then the output, we are getting the output at high frequencies. So this is the high pass filter. So we are giving these frequency responses to the adder. So adder is what the normal function of the adder. It will perform the arithmetical addition of these two responses. So whatever the signal for you are giving to this summer circuit or adder circuit. So for example, if you give like a 1 volt and 1 volt, so what this will do, summer will give at the output 2 volt, right? So it will just combine these or add these, whatever the input signal you are giving at the input. It will have multiple inputs. So maybe, so if we use this negative terminal for the feedback, so we are not using this one will be grounded. And so here we will have multiple input at the other arm. So that is a positive side. So here we have more than single input. So for example, here, or I can have 2 input, or I can have 3 input or 4 input. So it's really depending upon the application. So we can apply multiple inputs to the other input terminal of the operational amplifier. Then it will act as a summer circuit. So by adding these two responses, what we are getting at the output. So let me, so now I am adding these together with the adder. Then at the output, what I am getting. So this is the low frequency response, and we know this is the high frequency response. So we are only after this cross section of the frequency response of low pass filter and high pass filter. This is the low pass filter and this is the high pass filter response, and we are adding together with the adder. So we get the overlap at the output. So this region. So this region will be eliminated or stopped, band stop, and we get this at the output. Okay, this is how this band stop filter is working. So if you just transfer this block diagram based circuit from this component based circuit, so you can see here this high pass filter, we know how the high pass filter is. So we have the capacitor in series, and then this resistor is grounded or in parallel connection. So this is connected to this positive terminal of this operational amplifier, and this one is acting like a buffer circuit because we do not have any feedback resistor and input resistor. So this is the complete high pass filter, active high pass filter. And here we have the active low pass filter. So active low pass filter, what we are doing, the component location is different. So here, for example, this resistor, this is the RL. So the resistor is in the series and the capacitor is in parallel. So it's the other end is grounded, and we are giving the output of this low pass filter to the positive terminal of the operational amplifier, and we have this unity feedback loop, and we are getting the output, and we are using simple resistors, and then we are combining this together because this is the multiple inputs. For example, here we have the negative input terminal, positive input terminal. This is the summer circuit, right? So in the summer circuit, one terminal got grounded, the other terminal we can get multiple inputs. So we are applying this V in 1 via R1. So V in 1 is the first input, and this is the V in 2 is the second input. So we are applying through this input resistor R1 and R2 to this terminal. So actually this one will add these two responses at the output. So same like this, and then it will reject this specific frequency range, and then it will pass the rest of the frequencies. So band stop or band elimination filter. So the summing of the high pass and low pass filter means their frequency responses do not overlap, unlike the band pass filter. The band pass filter, it's the opposite operation. So the band pass filter is the totally opposite. The band stop, we are just eliminating specific frequencies by using the summer circuit. For example, we have a first order low pass filter with a cutoff frequency FL, that is 200 Hertz, which is connected in parallel with the first order high pass filter. This is the first order high pass filter and this is the first order low pass filter. Why we call this is a first order? Because we have only one stage or one pole. So then we will just see the rest. This first order high pass filter with the cutoff frequency, that is the FH is equal to 800 Hertz. When these two filters are connected in parallel, the input signal is applied to both filters simultaneously as shown in the figure. So we are giving common input signal, same input signal to this high pass filter and also the low pass filter. So maybe this can be like a 1 to 100 kilohertz. I am applying the same signal in parallel to these two filters and I'm getting the output. Okay. So then I get the frequency response of these two filters. So all input frequencies below 200 Hertz, that is going to be less than 200 Hertz. Okay, so in this example, we are talking about these 200 Hertz and 800 Hertz. So then in that case, now we can say like a 1 to 1000 Hertz we are applying at the input. So whatever the frequencies which are less than 200 kilohertz would be passed to the output by this low pass filter. So I am applying this much. The low pass filter is only passing up 1 to 200. The unit I used hertz here, so we can just keep hertz, not the kilohertz. So it will allow 1 to 200 hertz at the output. This is the low pass filter. So it's passing only the low frequencies. And the high pass filter, what it will do? So input frequencies above 800 hertz, it will be passed by this high pass filter. So it will pass whatever the frequency is more than 800 hertz, it will be passed at the output of this high pass filter. So however, an input signal frequencies in between these two frequency cutoff points. So we know the cutoff frequency of this one is 200 hertz and the cutoff frequency of this stage is 800 hertz. So the frequency between this 800 and 200, what will happen? So that is what mentioned here. The input signal frequencies between these two frequency cutoff points, that is 800 minus 200, that is 600 hertz bandwidth, it will be rejected by the summer at the output. So this is what I mentioned here in this one. So this one is passing only low frequencies and this one is passing only high frequencies. By adding them together with the help of this summer circuit, then we reject this in between frequencies. So 600 hertz is too high to be passed through this LPF. Yes, because it will only pass this up to 200 hertz. It cannot pass these high frequencies. And similarly here, this high pass filter cannot pass whatever less than this 800 hertz. It can pass only above this 800 hertz. So it's very obvious, you can see, even though I apply 1 to 1000 hertz, I am getting only from 800 hertz to 1000 hertz here at the output. And here I am getting only from 1 to 200 hertz at the output. So I reject between 201 to 799 hertz. I reject. So I do not get these frequencies at the output. So now I am combining this by using the summer circuit and I'm getting this output. So this is what we want. So we want to reject certain frequency range and we want to only allow the rest of the frequencies. So I had given just this numerical example so you can understand the function of this band stop filter. Okay, so 600 hertz is too high to be passed through this LPF, and 600 hertz is too low for this high pass filter. So this just you can say this 600 hertz cannot pass through this low pass filter because this kind of middle range frequencies. These 600 hertz cannot be passed through this high pass filter because this is also in the middle frequency range. So these cutoff frequency values are depending upon R and C values. So you have cutoff frequency 200 hertz here, and you have cutoff frequency 800 hertz here. So you can change this value by changing these R and C values. That we know that already. So because the formula is 1 divided by 2 pi RC. So if you are after this low pass filter cutoff frequency, then of course you have to change this CL and HL value. And if you want to change the cutoff frequency, the high pass filter FH, then you have to change the corresponding R and C value, 2 pi RC. So here is CH RH. So RH CH. So you have to change these two values to change the cutoff frequencies. So then, for example, by changing this one, maybe you can make this as a 700 hertz. And then it will pass whatever the frequency comes more than or greater than the 700 hertz, it will pass through. And whatever the frequency here, if you change this one to 300 hertz, that's the cutoff frequency. So whatever the frequencies which is less than this 300 hertz can pass through, the rest will be blocked. Here the opposite. So by this way, you can design this band stop filter.